Hello, everyone, and welcome to a new session of Surfing the Ocean. Today, we have the pleasure of welcoming Francisca, a PhD student at UC Berkeley, under the supervision of Mike, who's going to introduce you to the quantum field and is going to talk a little bit about finding Nash equilibrium and its quadratic speedup. The floor is yours.
All right. Thank you so much, Antonia, and thank you for inviting me to speak at this great seminar. I'm really happy to present this work, done with a bunch of really great collaborators, Manolis, Panagiotis, Georgios, and Mike. Um, so I was told in advance that the general audience of this seminar does not have a ton of quantum background or might work in fields that are not too quantum related. So my goal for this talk is going to be to try and introduce the basic quantum that you'll need to be able to understand the result and then give kind of an overview of the result. Um, I want to also say that this result isn't necessarily extremely quantum for folks who are really familiar with standard classical algorithms for finding Nash equilibria. Really, this result is kind of saying that while in standard classical games, we have efficient algorithms for finding Nash equilibria in the simplex. This result in moving to the quantum setting is really talking about our ability to find Nash equilibria in a more general, complicated, higher dimensional space called the spectraplex. So I'll go into all of this in the course of my talk, but just as a general disclaimer, my primary background and most of my research is in quantum. I'm definitely far from an expert in economics, game theory, hardcore optimization theory. So I'll try my best to answer any questions you may have, but apologies in advance if there are advanced topics you all know about that I'm not as familiar with. All right, so with that, I want to start off by presenting an overview of the main results of the paper. So, at its core, the focus of this paper is really the proposal of a novel algorithm that we call optimistics matrix multiplicative weights updates for finding approximate Nash equilibria of quantum zero-sum games. And to do so, we leverage a new kind of gradient-based view of quantum zero-sum games, which matches more closely to how we view games in the classical setting. And in leveraging this novel perspective, this enables us to utilize optimization techniques from the classical games literature. In particular, we are able to prove that optimistics matrix multiplicative weight updates achieves an order 1 over epsilon iteration complexity to find Nash equilibrium epsilon approximate to find epsilon approximate Nash equilibria of quantum games. And this is actually a quadratic speedup relative to the best prior algorithm, one proposed by Rahul Jain and John Watrous back in 2009. In particular, we leveraged the proof technique of NA and Nguyen from 2020 for monotone variational inequalities to achieve this bound. We further introduce a design framework for quantum zero-sum game algorithms, which we use to unify the quantum zero-sum game algorithm landscape and motivate the development of OMMWU, as well as kind of compare it to the Jane-Watrous algorithm and a number of intermediate algorithms along the way. All right, so this is a high-level overview of the paper, but as I mentioned, I want to take a bit of time kind of just giving background on the relevant quantum that you'll need in order to understand the different concepts I'll be talking about throughout this talk. So to start off with, I'm going to introduce a bit of notation that we use in quantum. Specifically, in quantum mechanics, we often use this notation called Dirac notation. It was invented by Dirac, and it's a bit of a funny notation, as you'll see in just a bit. So really, it's just an alternative way of doing linear algebra in the setting we use it. So the first object of interest is something called a ket, which is really just a column vector. And we denote it by taking whatever the standard letters you would use to denote a vector, and we throw it inside this funny looking bracket. Now, a common other object we need in quantum mechanics is the conjugate transpose of these vectors, which we typically refer to as a bra. And you denote that by just flipping the bracket denoting a ket around. Now, the reason why these objects have these funny names is that when you then look at, for example, the inner product, which is a constant value, and you write it out, well, that's the conjugate transpose times the vector. So you get what is then a bracket. And it looks, I guess, a bit like a bracket. And then finally, if you have an outer product, the name isn't as satisfying. It's a ket bra, but just to say, if you see uh, the bracket in the other direction, you should think of it as a matrix. And this notation is kind of nice because in quantum mechanics, we often have long series of vectors and matrices we're multiplying, and it kind of quickly allows you to identify where you have maybe a constant value versus a matrix when you're trying to shuffle things around. Um, all right, so that's just a bit of notation. Hopefully this is clear, but of course I'm giving a very quick overview of quantum, so if there are any questions or you want me to slow down, feel free to let me know. So with that, we'll now jump into the notion of a quantum state. And to introduce quantum states, I want to first talk a little bit about classical bits. So when we think of classical bits, we generally think of them as taking two values, either 0 or 1. And in the quantum setting, we're going to represent these as basis vectors. So in particular, the 0 bit will be denoted by the two-dimensional vector 1, 0, and the 1 bit will be denoted by the two-dimensional vector 0, 1. And you can already immediately see that these two bits in a two-dimensional complex space form an orthonormal basis. And so typically in quantum mechanics, we'll think of classical states as being basis elements of the full space spanned by quantum states. To to explain this a bit more formally, we say that quantum bits are normalized complex linear combinations of classical bits. The quantum term for this is a superposition. And so really all this is saying is if you have some quantum state phi, you can express it as a linear combination of the classical bit states, which are these basis vectors, where the coefficients, importantly, are complex valued, and the sum of their norm squared adds up to 1. We'll discuss in just a little bit that these coefficients have a special interpretation as probability amplitudes relating to your likelihood of measuring a given basis element. But before I get into that, I just want to talk about the generalization of bits to bit strings. So classical bit strings are then going to be combinations of classical bits, which mathematically in this quantum framework we represent with the Kronecker tensor product. So for example, if you take two zero vectors and you do a tensor product, you get a larger 2 to the 2 dimensional vector of this form. And we can similarly calculate this for all of the other 2-bit classical bit strings, and you can generalize this to sequence of n bit strings. And so again, with this intuition that quantum states are really kind of just linear combinations of these classical bit string basis elements, we get that quantum states are just superpositions of classical bit strings. So in particular, a quantum state in its most general form is just a sum of, or a linear combination of these classical bit string basis elements, where again, we have this condition that the coefficients are complex valued and their sum squared equals 1. And with that, we'll now segue into this notion of quantum measurement. So when we measure a quantum state, we say that it collapses to a classical state. And so recalling from the last slide that quantum states have this form where they're in a linear superposition over classical basis, classical bit strings. What's going to happen when we perform a measurement is that this quantum state is going to actually have to collapse to just one of the classical bit strings that it's comprised of. And this is going to be a probabilistic phenomena. So every time we measure we'll expect to probably see a different classical bit string, and the likelihood of observing any given bit string is going to be governed by these probability amplitudes. So in particular, the probability that some state psi collapses to a bit string x is given by the amplitude squared corresponding to that bit string x. And so just to give some examples of some basic 2-qubit states, I have a plot here showing, for example, if you have a state psi1 that's just fully in the zero state, if you perform repeated measurement, you're always going to get the same outcome. However, the second state is what's commonly known as a Bell state. It's kind of maximally entangled between 0, 0 and 1, 1. And when we measure it, we're going to have 1/2 probability of observing either the 0, 0 or the 1, 1 outcome. Meanwhile, this final state, oh, there's a typo, it should be psi3, but it's in a uniform superposition over all the classical bit strings. So when we measure it, we'll have equal likelihood of observing any classical bit string. So this is at the core kind of how quantum measurement works. I'm not really in this talk going to try and explain why things work this way, but just laying out the math, and hopefully you all can assume it's true, and we'll use this later in the talk. So there's one more thing I kind of need to discuss, which is the notion of a mixed state. So far we have kind of described what are commonly called pure quantum states, which is a valid quantum state, but it's under this assumption that you know exactly what state your quantum system is in, which is something we can do in theory, but in practice, a lot of the time you'll have epistemic or classical uncertainty as to which state our system is in. And so the question you might ask is how you can kind of deal with that and represent that mathematically. So in quantum mechanics, we typically represent classical ensembles of quantum states via these objects known as density matrices. So density matrices are probabilistic mixtures of pure states, where you now take each of these pure quantum states and you create a convex linear combination of them, where now your coefficients are just probability values that are going to sum to 1. And density matrices formally have 3 key properties that they satisfy. The first is that they're Hermitian, so the conjugate transpose of the matrix is equivalent to itself. They're positive semi-definite, meaning all the eigenvalues are non-negative. And finally, they're trace 1. And this is kind of the normalization condition that imposes that they correspond to valid probability distributions. And I kind of hinted at this when I was at the very start of the talk, but the space that we'll be interested when we're looking at these quantum zero-sum games is a space known as the spectraplex. And this is kind of just a fancy term in convex geometry for basically the space of all possible density matrices.
So is this a generalization of B-stochastic? No, it's not B-stochastic, sorry. It's more complicated than that. It's because you have Hermitian. It's more complicated than B-stochastic than what you have there, right?
So I'm not too familiar with
Do you need that because since you have that you need to sum at 1, okay? B-stochastic would be that you need to sum at 1 all the rows and all the columns needs to sum at 1, and so this is why they use as the transition matrices. But since here you have a Hermitian also, like this is much more complicated than that, so you have a lot more structure maybe.
Yeah, I guess also everything here is kind of complex valued, which oftentimes leads to some complications relative to thinking about things from like more classical probability theory. One of the main kind of quantum complexity theorists in the field, Scott Aaronson, he likes to claim that quantum mechanics, quantum computation is really just complex probability theory under the hood. And so a lot of the interesting phenomena that happen in quantum are because of interference that emerges from these underlying complex numbers in the objects we deal with. But thanks for the question.
Thanks.
All right, so we've now kind of talked about how to generalize quantum states in this setting where you have uncertainty, a classical uncertainty as to which quantum state the system is in. Um, Now I want to talk about how you can describe measurement in this more general framework. And so the generalization of quantum measurement is known as positive operator valued measures, or POVMs for short. And POVMs are basically just collections of PSD operators that satisfy a completeness condition, essentially saying that they sum to the identity. And each of the operators in this set is going to correspond to a measurement outcome, in our case, a finite set of different possible measurement outcomes. There are also, I think, infinite dimensional generalizations, but that's not too relevant to us for this talk. And so the probability of obtaining some specific outcome omega when measuring a state rho is going to be given by the trace of the POVM operator, P sub omega, multiplied by rho. And so the last kind of quantum thing I need to define is this notion of an observable, which is going to allow us to attribute a reward in this more game theoretic setting for each corresponding to each of the measurement outcomes. So in particular, an observable is just going to be a linear combination of POVM elements corresponding to each of the outcomes we're interested, multiplied by a reward corresponding to that specific outcome. And the reason why observables are interesting is that they give us a way to describe the expected reward for repeatedly measuring a given mixed state. So if we take some density matrix rho and we calculate trace of O rho, this will give us the expected reward relative to this observable for this measurement. All right, so I think that's all the background I wanted to give on quantum mechanics. If there are no questions, I'll move into the talk and we'll see all of these concepts again, now in a more kind of game theoretic setting. All right, so the title of this talk is A Quadratic Speedup in Finding Nash Equilibria of Quantum Zero-Sum Games, which I recognize is very long. So my plan for this talk is to kind of break it down. And to start off with, I'm just going to introduce the notion of a quantum zero-sum game. So what is a quantum zero-sum game? Well, it's going to be a two-player game. In quantum, we love calling our players Alice and Bob. And in each round, Alice and Bob are going to play unentangled mixed states, which kind of each lie in small n and m dimensional spectroplexes. And when I say untangled, you can really just think of that as the states being kind of uncorrelated. So Alice and Bob don't really share any information. They're in their own separate rooms on opposite sides of the world. They prepare their states. But then when they play the game, they're going to both send their states to Roger, who will now have a joint state. And we're going to call Roger the game's referee. Because Roger is now going to make a measurement with respect to both of their states, so a joint measurement, and Roger's going to have a special payoff observable. So we just saw how using this POVM framework for all different outcomes, you can assign different rewards. And this is a way you can kind of map the standard concept of rewards from the classical game setting into the quantum setting. And so based on the measurement outcome, so the expected reward, the referee, Roger, is going to send rewards back to the players, Alice and Bob. And because this is a zero-sum game, one of the players' wins has to be the other player's loss. So if Alice makes a certain amount of money, Bob is going to have to lose that amount of money. All right, so now we can describe game strategies and expected payoff. As I mentioned earlier, classical zero-sum games are typically played in the simplex, which you could think of as being points corresponding to different strategies. And players in classical games often play indeterministic strategies, which now correspond to probability vectors over each of the individual strategies they could choose to play. So the notion of expected utility for a specific strategy is calculated by just taking this like payoff observable matrix and doing an inner product with the strategies of the two players. In the quantum setting, however, quantum zero-sum games, as we mentioned, are played in the spectraplex. And so if, for example, we were playing a game where there's just two different possible strategies, you would have these 2 points, but the space of, I guess, all the possible indeterministic strategies that the players could play would then be this more general object, which in quantum mechanics we typically call the Bloch sphere. And so players are going to play mixtures of indeterministic strategies or meta strategies encapsulated by these density matrix objects we discussed. Because kind of in our discussion, right, we said that pure quantum states themselves are kind of probability distributions over classical outcomes. So those are, in some sense, analogous to the indeterministic strategies in the classical setting. But then you have this added layer of probability because you have uncertainty in the quantum state you're playing itself. So there's kind of in the quantum setting a second layer of probability or uncertainty going on. And we can calculate the expected utility for a specific set of strategies from Alice and Bob by taking the trace of this observable with respect to the tensor of Alice and Bob's state. All right, and so the objective in a quantum zero-sum game is determined in part by the expected payoff. And so, as mentioned, we know that if Alice's expected payoff is some value u, because it's a zero-sum game, Bob's expected payoff is going to be the negative value. And in playing the game, each player is going to want to maximize their expected payoff. So Alice wants to maximize this quantity u, whereas since Bob is going to receive the negative value, he's going to want to minimize the quantity u. And these are competing interests, which are going to define a minimax optimization problem, which we typically think of as being a saddle point problem.
Francesca?
Yes.
So just to make sure I understand, can I think of like the actions of so basically it's a two-player game, right? Where the space of action that each player are playing is like more complex. Can I think about it as some kind of like distribution over the space of distributions in some sense, like some kind of random measures that are being played?
Yes, that's like exactly how I think about it. There is a bit of complexity, again, because you have these complex values, which are a bit different from the classical setting. And I think I'll mention in just a bit, there's some cool work by David Meyer from the 90s where he shows that you can actually get advantages playing quantum strategies over classical strategies and different types of games by leveraging interference properties that emerge because of these complex values. But for now, yeah, we just think of it as a more complicated space, encapsulating these distributions of distributions.
So it's some kind of like infinite dimensional game with some structure which is taken from the quantum application in some sense.
Yes, exactly. All right, thank you. So one question you might ask is why should we care about or want to study these quantum games? And it turns out that general quantum games have emerged in many different areas of quantum information. So among the biggest results in quantum information of the last decade was this MIP star equals RE result, establishing the power of quantum computation. And it fundamentally was a result about non-local games. There are also these very interesting notions of quantum interactive proofs, which can be viewed as competitive refereed quantum games. There's also multi-prover quantum interactive proofs, which are more like cooperative quantum games. There are interesting results on quantum coin flipping, which can be viewed as two-player quantum games. But in general, there is a result stating that optimization of general games is actually p-pad complete. So we shouldn't be able to solve these quantum games in general. which is a pretty big limitation. So this then leads us to ask why study quantum zero-sum games in particular. Although general quantum games are p-pad complete, quantum zero-sum game optimization is computationally tractable, as is the case in the classical setting. And in 2009, Jane and Watrous proposed an explicit quantum zero-sum game algorithm that converges to an epsilon approximate solution in order 1 over epsilon squared iterations. There are many uses for these quantum zero-sum games. So namely in game theory, as I was just mentioning, David Meyer was able to prove that quantum strategies can actually be better than classical strategies in certain games, specifically in this quantum zero-sum game setting. In terms of complexity, Jane and Watrous actually use this quantum zero-sum game algorithm that they established to prove that QRG1, the space of quantum refereed games, is contained in P space. And then finally, in the machine learning setting, there's been recent interesting work and excitement about quantum generative adversarial networks, which you can model as a quantum zero-sum game. All right, so now that we've defined the notion of a quantum zero-sum game and seen some reasons why we might be interested in them, I want to talk a bit about finding Nash equilibria. So the solutions or fixed points of the minimax defined by the game's value are as depicted on the slide. We know that the min of the max is equivalent to the max of the min by von Neumann's minimax theorem. And Nash equilibria are basically just game states such that neither player has an incentive to change to another state unilaterally. So for example, if Alice was to try and deviate from the Nash equilibria, the utility would, or the expected payoff would decrease and Alice would end up losing money. And similarly, if Bob was to deviate from this Nash equilibria, the expected payoff would increase, but since Bob is getting the negative of that, he would also end up losing money. So algorithmically, we're going to view the problem of finding Nash equilibria as an online learning problem. In each of the round, each of the players, Alice and Bob, are going to query this referee, Roger, that we'll view as an oracle with a state. In each round of playing the game, the referee is then going to return feedback to each of the players, and the players are going to use this feedback to update and improve their states so as to try and maximize the reward or money they earn. And the goal is to try and minimize the number of rounds until the players both reach an epsilon approximate Nash equilibrium. All right, and so this was probably a review for many of you, but now I'm going to go into kind of one of the key points of our work, which was taking a more gradient-based view of quantum zero-sum games. So previous work on quantum zero-sum games characterized the game's feedback via a very common object in quantum mechanics known as a superoperator. So in particular, Alice's feedback was described by the superoperator object, which involves taking a partial trace over the payoff observable multiplied by like the identity on Alice's state tensor with Bob's state. It's not too important for this work, exactly how these superoperators work, because in this work, we actually move away from this more physics-based view, instead characterizing the game's feedback via gradient-based operators that more closely mimic how we view things in the classical setting. So instead, in our paper, we chose to view Alice's feedback via a gradient of the expected payoff. So Alice's feedback will be the gradient with respect to the state that Alice plays, and Bob's feedback will be the gradient with respect to the state he plays. And it turns out that these two characterizations, either the superoperator or gradient-based view, are equivalent. And you can probably see this directly just from the expressions I wrote out, but explicitly, we have that Alice's payoff is exactly equivalent in expected payoff is exactly equivalent between the two cases if we multiply Alice's state either via this gradient-based operator or the super operator. And Bob's expected payoff is almost essentially equivalent. We just need to add a negative sign in the super operator case to make it equivalent to the gradient-based setting. And so the reason why moving to this gradient-based view was so perspective or was so important was that it allowed us to formulate the quantum zero-sum game as a variational inequality. So specifically, with this gradient-based feedback, the expected payoff can now be viewed as a directional derivative. So the directional derivative in Alice's direction is kind of governed by this trace of a state times Alice's feedback or this gradient-based operation. And similarly, we can view the expected payoff as a directional derivative in Bob's direction. Now, when we look at the joint state, we have a directional derivative corresponding to both Alice and Bob states, which allows us to characterize the game's equilibria as solutions of the following variational inequality comprised of the joint states. Graphically, this can be depicted as followed. The kind of key idea is that you have this spectraplex consisting of all of the player's states, and the gradient needs to be orthogonal or pointing outside of the space. It's going to be tangent to the space, so this implies that the inner product between an optimal solution, which should lie at the edge of the spectraplex space, since we want it to be as close as possible, is going to have to be non-positive value. And so in addition to characterizing the game as a variational inequality, by formulating the feedback from this gradient-based perspective, we're able to prove that this F operator is monotone and Lipschitz, which offers some very important additional structure about the game that we can use to leverage efficient classical algorithms for solving monotone Lipschitz variational inequalities. And this was really one of the keys to establishing the quadratic speedup in our work over the prior work. So with that, I'll now jump into explicitly
Sorry,
describing.
can you go back just 1 second? Can you go back?
Yes.
Like you said that like this monotonicity is like under some assumption on the it's given under some assumption on U. What, and if so, what are the assumption on U? Like, because there is there's a variational inequality is linked with the directional derivative of the utility U, and therefore how this is linked with the monotonicity. So is this a general result or?
So I guess maybe I'm not fully understanding the.
You said that you characterize that F is monotone and Lipschitz, but like, is this under specific assumption on U, or is it the structure of the problem that make it F always monotone and Lipschitz?
So we show that it's the structure of these like quantum games that make it this way. We have a proof in the appendix. I specifically proved it by doing poly analysis, so decomposing this operator in terms of like an orthonormal set of matrix spaces and proving this. My co-author said there are probably more direct ways, just following the classical proofs for proving monotonicity of classical game operators. But yeah, we don't really have too many constraints on what the payoff observable is. I don't remember off the top of my head. I think there were some kind of obvious ones, like you can't have like infinitely large payoffs, so it has to be finite, and it might need to also be bounded, if I'm remembering correctly. I don't know if it needs to be maybe non-negative, or I think in our case to also do the proofs, we might have assumed it was bounded between like 1 and -1, but I think that was the only assumption we had.
Okay, thank you.
Thanks for the question. All right, so now in terms of the quadratic speedup itself, really from the algorithmic perspective, the key to getting this quadratic speedup was moving from gradient to mirror to proximal descent. So I'll start off just by quickly describing gradient and mirror descent, and then introducing our algorithm. So we're all familiar with, I guess, classical gradient descent, which allows us to find maxima or minima by essentially just repeatedly subtracting off a gradient with respect to some function of interest. And equivalently, you could say that gradient descent minimizes the first order approximation of f with respect to a Euclidean regularizer. To generalize gradient descent to other regularizers, say some other function regularizer h that we're interested in, we perform what's commonly known as mirror descent, which has this form to it. And you can see that in the case where h is in fact the Euclidean norm, this gradient of h becomes y, and you get gradient descent in return. So mirror descent is kind of just a generalization of gradient descent for alternative regularizers. And pictorially, we can view it as mapping between a primal and a dual space, where we're going to have our primal state. We're going to take the gradient with respect to the regularizer of interest, apply it to our space state, and now in the dual space, we can simply subtract off this gradient, and we'll then map back into the primal space and continue doing updates of this form. And the reason I mention all of this is because actually the prior work, the Jane-Watchus algorithm, is an algorithm known as, which they call matrix multiplicative weight updates, or MMWU. And for those who are familiar, this is just a quantum generalization of the classical standard multiplicative weights update algorithm. It's matrix multiplicative weights because now you're operating over matrices. And in our work, taking this more optimization, mirror descent based perspective, we're able to show that MMWU is in fact just an instance of lazy mirror descent, where we call it lazy because instead of in every step mapping back into the primal state, they just kind of stay in the dual space and repeatedly do updates in the dual space and only move back into the primal space at the very end of the algorithm. But yeah, we show MMWU as this lazy mirror descent with a von Neumann entropy regularizer. And in the original work of Jane and Watrous, similar to the classical multiplicative weights update algorithm, they're able to prove an order 1 over epsilon squared convergence. Now, I want to point out that around the time that Jane and Watrous were working on this in the quantum setting, there was actually a fundamental misconception in the classical game theory literature, where many people believed that order 1 over epsilon squared was the best you could do for games in general. However, Nemirovsky in 2004 wrote a paper where he explicitly said that while this order 1 over epsilon squared convergence rate is optimal for black box optimization problems, you can actually achieve an order 1 over epsilon rate, specifically for instances of monotone variational inequalities. And so the way that this speedup is achieved is basically via two important concepts known as proximal steps and optimism. So to improve upon MMWU, we leverage what are called proximal instead of mirror steps, which introduce kind of a notion of momentum. So rather than kind of the standard mirror step where you move into the dual space and you come back into the primal space, do your gradient update, and it's all just one step. In a proximal step, you actually perform a secondary gradient update, which kind of does feedback or correction on the first gradient step. One of the key drawbacks, though, to these proximal steps is that they require two gradient calls or two oracle calls. So we further leverage a notion of optimism that reduces the total number of oracle calls from 2 to 1 by, instead of in every step repeatedly computing two gradients, we actually leverage gradient information from the prior step in the new step to do these updates. And I know this is all a bit fast, it's pretty technical, but we have discussion of it all in the paper. And so with that, our proposal for optimistic matrix multiplicative weights was really just leveraging proximal maps and optimism in the uh, in addition to the work done in the original matrix multiplicative weights updates algorithm. So our algorithmic proposal can be summarized via the two following steps, whereas the original matrix multiplicative weights update algorithm looks something of this form. And like classical optimistic weight multiplicative weight updates, we're able to prove an order 1 over epsilon convergence for worst case games. So the proof follows from the proof structure of Nguyen from 2020 for monotone variational inequalities. And in particular, we leverage notions of strong convexity, smoothness, and Fenchel conjugacy to prove this result. So as I mentioned on the last slide, overall, this proof that we do really only is applicable to worst case games. And you might say, okay, you have a quadratic speedup for worst case games, but what about the average case performance? So to assess that, we run a series of experiments where we generated 50 random games, ran them for 50,000 iterations, and compared OMMWU to MMWU. And we had a few important experimental findings. The first was that we found OMMW was significantly more numerically stable than an MMWU. In trying to run MMWU as a baseline, it at some point would always just go kind of haywire and start blowing up because of numerical instability. So I tried implementing some variants of MMWU with like step size decay and stuff like that to make it more competitive. But OMMWU just converged and worked very cleanly straight off the bat without any modifications necessary. And then second, we found that OMMWU did in fact retain what appeared to be a quadratic speedup even for these randomly generated average case games. So that was pretty cool to see. And I'm just about to finish up. I just want to briefly describe kind of the algorithm design for quantum zero-sum games to sort of unify the landscape and show explicitly how we got to this OMMWU proposal. So specifically, we started off by taking this proposal by Jane and Watrous, their matrix multiplicative weight updates, and we were able to show that this is a special instance of a more general class or family of algorithms known as matrix dual averaging, where they specifically use an entropy regularizer. It turns out that this was a pretty good choice if you were to instead parameterize this matrix dual averaging framework with, say, for example, a Euclidean L2 norm. You would get a much worse dependence on the dimensionality. So it would have an exponential dimension dependence, whereas the entropy regularizer gets a linear dependence in the dimension, which is great. However, it has the key drawback that it requires order 1 over epsilon squared iterations to converge to the Nash equilibria. So we then move away from mirror descent to proximal descent, which enables us to propose a framework known as that we call matrix mirror prox. And then we again show the resultant algorithms that emerge if you were to parameterize this with an L2 norm or an entropy norm. You again retain the good dimension dependence if you use the entropy regularizer in this framework, and you're able to now achieve this order 1 over epsilon iteration complexity, which is great. But the key drawback is that these matrix mirror prox methods require 2 gradient calls per iteration or 2 oracle calls. So this then leads us to introduce a notion of optimism in which we reuse our gradient calls from the previous iteration. So this brings us back from 2 gradient calls down to 1. And again, we, in using the entropy regularizer, retain the optimal dimensionality dependence and the good iteration complexity. So this is kind of the algorithmic design landscape we explored in our work and motivates really how we got from this original Jane-Watrous algorithm proposal to our proposed optimistic matrix multiplicative weights updates. Um, so that's all I had today. Thank you all so much for listening to the talk and your great questions. I'm happy to take more now if you might have any.
Thank you very much, Francisca, for the amazing talk. Like you condensed a lot of different topics in like 45 minutes. Like really, thank you. So, are there any questions? Maybe I can start with some. So I have two questions maybe. Like the first one is um if you were not to have this strong this these nice features, this nice property on your function f, um would everything collapse?
Yeah, so that's a really good question. So if you don't have these nice properties of monotonicity and Lipschitzness, unless there was some other structure that you could leverage, you would have to treat it as one of these kind of black box games and assume that order 1 over epsilon squared would probably be the best you could achieve and that the Jane-Watrous algorithm was in fact optimal. So really kind of the key insight of this work, I would say, was that we moved into this gradient-based view of quantum zero-sum games where we were able to then explicitly prove monotonicity and Lipschitzness of this operator because in the original, I guess, super operator perspective that Jane and Watrous were using, you could then actually interpret monotonicity and Lipschitzness as having things to do with like the complete positive trace preserving nature of the maps they're using and things like that. But it becomes a lot less straightforward to see. So really, in moving into this gradient-based view, uh, we had a nice mathematical object we could prove this structure for. And then because of this structure, we were then able to take the classical algorithm that exists for getting the improved convergence rate and speed in the classical setting and show that it then extends to the quantum setting. So to answer your question, I think if we didn't have this nice monotone Lipschitz property, then we wouldn't necessarily expect to be able to achieve a 1 over epsilon convergence rate.
But would you think that he would still perform somehow well? Because you said that like in the way you have developed like a state of the art, the previous approach to your setting, like you were able to prove that everything was working well because of these nice properties. But maybe if you didn't have like this nice property, maybe it would still be okay somehow. Do you know if it makes sense? Because you said like you exploit like this proximal methods, so maybe you would still be better on the constants or like on the speed of convergence somehow, even if not if you maybe even if not dramatically better as you proved in this one. I don't know if it makes sense, but
Yeah, no, I think I see what you're saying, and potentially, I would expect that the proximal method would give advantages, but because it's like when you go into the sorry, let me see if I can go back to the experiment slide. There is an overhead though for running these proximal methods, which is that the runtime doubles. So you would have to be a bit careful if you're looking at, say, shaving constant factors to make sure that the overhead you incur by running this more complicated algorithm doesn't then surpass the kind of gains you would get in other areas.
okay. And so that's linked to my second question I want to ask is do this like using two steps of the gradient like just accelerate, or it does also stabilize your kind of learning? That's maybe the question.
Yeah, so I think it does both. It accelerates and stabilizes. I think Mike has much better intuition for
Mhm.
the picture of this proximal step because I think you can view things as like decaying inward and exploding outward, and doing these proximal gradient updates allows you to circle in a much nicer fashion. But I don't personally have the best intuition for these like dynamics. I think though, in terms of our experiments, we got the numerical stability in part because like in the standard matrix multiplicative weights update, they do a division where if you have eigenvalues very close to zero, things start to blow up, and those nicely don't appear in the implementation of the optimistic algorithm.
Okay. Okay. Well, thank you very much. Well, if there are no other questions, maybe we can thank Francisca again and like stay tuned for another session of Surfing the Ocean. Thank you. Bye
All right.
bye.
Thanks, everyone.